Today we're going to talk about the concept of the Lagrange multiplier, which is used to find maximums and minimums of a cost function and its constraints. Now, what do I mean by a cost function and a constraint function? And what do I mean by maximums and minimums? Well, let's start with maximums and minimums, particularly local maximums and minimums. So let's get a different color in here for that. Let's go for black. Okay. All right. So say that we have a function that's just of one variable. So we have x, and then we have f of x up here. And this function looks in some weird way, right? Well, you could pick a point and say that, this is the maximum, that's it. But there's another local maximum right here, and another local maximum right here, and another local maximum right here. And you can sort of just intuit what local maximum means from that. It means just the maximum that's right where that's at. In that little part of that function, that is the maximum. Okay. Now we have local minimums as well, just the same as we have local maximum. And all of these points are considered critical points. All right, so now we know what critical points are, at least in 2D. Let's think about what they might look like in 3D. Well, in 3D, say that a function just looks like some rolling hills, right? Then the peaks of those hills might be local maximums, and then the bottom of those valleys would be local minimums. So I think you get the idea. So let's look at a three-dimensional function. But instead of just finding the local maximums and minimums of this function, what Lagrange multipliers are useful for is finding the local maximums and minimums of the intersection between two functions, right? So we're going to call this function, we're going to call it our blue function, we're going to call it our cost function. We're going to call it f of x, y. All right, that's this function right here. And then we're going to impose on that cost function, we're going to impose a constraint function, right? We're going to draw this in red. And let's just say that it looks like a plane. Yeah. Say that it goes behind here. And try to make a straight dotted line, relatively straight. All right. All right. Okay, so this is a constraint function. We'll call this g of x, y. Now, what the constraint function constrains this function to is the intersection between those two functions. And that intersection takes place, right? We can sort of sketch out what that intersection might look like. It takes place right here. It's kind of an oval shape, right? And we can see by looking, straight on at this that, if we were to draw out our axes here to start with, let's say that this is our x-axis, this is our y-axis, and this is our f of xy axis, right? Or g of xy. F of xy and g of xy are the same units here, right? So we can see that these points right here and here, let's go ahead and highlight them in green, why not? Right here and right here are both going to be critical points. This one's your local maximum and this one's your local minimum. Now, how do we find those mathematically? We've already found them now geometrically by drawing it out. You can plainly see where they are, but how do we find them mathematically? Before we get into this section, I would highly encourage you to go back and watch my video on gradients and the gradient function. I would also encourage you to watch my video on the level curve function, because now we're going to take both level curves and gradients and put them together to describe how we can find these critical points. I assume that you know what level curves are, and I assume that you know what gradients are at this point. So let's go ahead and just as a little bit of a refresher, we're going to pick some points on this graph, and we're going to draw level curves and gradients for each of these functions. To make it a little bit clearer, I'm going to open a new blank sheet here, and we're gonna draw this plane individually, right? So that we can see what's going on here. So the plane is sloped upwards, right? So if we pick a point on the plane, let's say that we pick a point right here, right? If we wanted to find a level curve where we're not going uphill or downhill, we're going side to side, right? It's going to be a straight line cutting across the plane that's sort of perpendicular to the slope of the plane. Now, the gradient at this point is going to point in the direction of steepest descent. But it doesn't point in the direction with three components. It doesn't have an upward z component. It's like a compass. If you were standing on the side of a hill and you wanted to know which way was up, and it only points in directions that are along the xy plane. It doesn't point up the hill, but that's enough to point you in the direction of steepest descent. Now, the magnitude of that vector corresponds with how steep that direction is, but the direction of it itself only has x and y components. So we're going to draw it like this, right? It only has x and y components. If it had z components, it would look something like this, right? But it doesn't. So it has x and y components, and it's worth it to note that that right there is a 90-degree angle, and that's a 90-degree angle as well. Okay, so this is our gradient at this point, and this is our level curve at that point. Now, let's look at our, let's go back to black. Let's look at, oh man, that looks terrible. Let's look at our parabola. I guess that looks all right. That's sort of the back side of the parabola. Okay, so that we pick a point on this parabola. Right, so this point's on the front side of the parabola, the side that's facing us. Well, if we wanted to travel uphill, we'd kind of be going, up like this. So the direction which we'd be going, the direction vector points out this way. And it's a long vector because it's very steep, right? And say that we pick this point right here. Then we get a vector that points out this way for our gradient. Now, I skipped over level curves, so let's go back and draw some level curves for these points. Now, if we didn't want to go uphill at all, we'd sort of trace a path around here. And there's our level curve for each of those points. Okay, enough of a review. Let's go back to the intersection of these two graphs. Now, the points that we're interested in analyzing are the points along this curve, this intersection, right? So, let's do that. We're particularly interested in not just any of these points. We're interested in the critical points. And since, we've already found them geometrically, let's just go ahead and, say that we have them and go ahead and draw the level curve through it, right? Each of these. Let's go ahead and draw their level curves. Now that's interesting. They are tangential. They are tangential to the intersection of the two functions. Okay, well, maybe we can do something with that. Now, let's go ahead and draw the gradient vectors at these points as well. And this is the critical thing to know. the gradient vector for the plane, let's see, we used red to describe the planes. Let's stick with that. The gradient vector is going to stick out this way, right, at both of these points. And the vector for the parabola is going to stick out. Let's go with blue. It's going to stick out in exactly the same direction. It's just going to be steeper in this spot. And then at this point down here, it actually points out in the opposite, the exact opposite, 180 degrees opposite direction at a different magnitude from the gradient of the plane. Okay, well, that's interesting. Does that happen at any other point along this intersection? No, it doesn't. And you can find that, one thing about a plane is the gradient's always going to be in the same direction, right? So at this point, the gradient goes out that way for the plane. Let's pick another point out here as well. Pick a third point just to prove our point. And let's go ahead and draw what the gradients would look like for the parabola at these points. They would look something like this, and even like this. None of those are parallel with each other. Only at critical points are they parallel. So, therefore, this is a great method of finding the critical points along this intersection curve. All right, so let's write out what this actually says mathematically, right? So let's say the gradient function of f is equal to some scalar, right? The scalar could be positive or negative, right? Some scalar multiplied by, not blue, this one's red, multiplied by the gradient of this function. So for any set of x and y values that satisfies this equation, you have a critical point at that x-y value pair. And this constant right here is your Lagrange multiplier. That's the special thing that allows us to figure out what these critical points are. Okay, now let's go and work on a few examples of actually implementing this, and that way you can get the hang of it.